Hey guys, we made it to the last section of chapter 11, finding the area of regular polygons. So some of these can get kind of tough.
Yeah, these do get a little bit tough. It involves a lot of different things and just an area where you're unfamiliar with this.
Yeah,
Really.
yeah.
So
Even though in chapter 8 we talked about regular polygons, we didn't go real in depth with them and
No.
kind of tear them apart like this first diagram does.
right, and it kind of like I said, there's a lot involved here.
Yeah.
And so and the formula is real general, but then it's got some elements that you've never heard of, and then when you're applying a radius to a polygon,
Something that's not a circle.
yeah, exactly,
Yeah.
and so that kind of throws the kids off. So
Yeah, yeah.
you know,
So we're looking at this first diagram here. And really this is critical.
yeah,
Because this talks about what you were just saying.
Yeah.
It breaks apart all the little pieces that you need to understand some vocabulary here.
yep,
So what they've done is they've taken, in this case, a regular hexagon. It really doesn't matter what the shape is. It's just a regular polygon. And they have inscribed it inside of a circle. Or in other words, circumscribed a circle about it to where the circle hits just the vertices. And so probably the biggest thing you need to see here is the PN, right there, the segment PN, would be a radius of that circle because it hits at one of the vertices, and again the circle hits at the vertices as well. And so that radius compared to the length of that segment PQ, which is obviously shorter than the radius, we have a specific name for that segment PQ, and it's called the apothem. Now, we've never had an apothem of anything before, and that, as far as I know, that's the only thing that term's ever used for, is
Yep.
that length from the center of a regular polygon to a perpendicular to a side of the polygon. And so in other words, it's the shortest distance out to a side of the polygon. So that's called the apothem. And notice that because we are dropping it perpendicular to the side of the polygon, that it always forms a right triangle, and that's critical because we're going to use that right triangle. And so we're kind of accumulating a few different things here. Now there's also something else here, because we skipped the chapter on circles to get to area because it's so important. There's also another concept here that we missed so far, and that would be angle MPN. MPN is called a central angle because it's at the center of the circle. And so that angle is a central angle, and we're going to be referring to that. But notice it's the whole angle of that big triangle. So angle MPN is a central angle here. Okay, we're going to use that angle in order to calculate something with that right triangle. And notice that red triangle there, basically, the bigger triangle, MPN, is an isosceles triangle because both of those red sides are radii of the polygon, and so they're equal to each other. So that is an isosceles triangle, and so that means that when you drop that perpendicular, it splits the triangle in half, splits the angles in half, all of that.
and it brings trig back into play.
And it brings trig back. Yeah.
Yep.
So you need to remember some of your trig from chapter 7. So.
And the thing that the guys, a lot of the times when you first start to see apothem radius, and kids get mixed up which one's which, the apothem always makes a right angle from the outside in, and a radius is always in the corner of the shape to the center of the shape,
Right.
basically. So just pay close attention to what the apothem is and what the radius is, because they really are going to be important to being able to do this.
Yeah, the radius is always going to be the hypotenuse of that triangle.
There you go.
It's always
That's
going to be
another
the
way to think of
longest
it.
side.
Yeah.
The apothem is always shorter. It's
Yep.
always one of the legs of the right triangle.
Yep.
So, all right. So, this example down here below, without some of the labeling in it, they're asking us to find some specific angles within that. And so this is important, guys, to see this example because it moves to the next one. And the next one is the critical one, or the next several examples that we do are the critical ones to understand this section. So first of all, they're asking us to find the measure of angle AFB. Now again, we just said from up above, that's a central angle. So we're trying to find the measure of that central angle. Well, that central angle, if you were to draw all of them, so BFC, CFD, DFE, and EFA, there are 5 of them because it's a pentagon in this particular case. In the diagram above, there'd be 6 central angles. And so there are 5 central angles inside of this circle, and so because the circle has 360 degrees in it, if you put all those together, if you drew all those central angles in there, it'd make 360 degrees. They're all equal because it's a regular pentagon. And so that measure of angle AFB would end up being just 360 divided by 5. And so that ends up being 72 degrees. Okay? So you just take 360 and basically divide it by how many sides there
That's
are in the
right.
shape, because
That's
that's how
the
many
easiest way to do
central
it.
angles there
Yep.
are. Okay? Now you need to notice that angle AFG, where AFG is, AFG, again, because that red triangle are the two sides of it being red, that's an isosceles triangle. When you drop that perpendicular, it splits it exactly in half. So that also splits that AFB exactly in half. So that 72 just gets split in half to give you the angle AFG, okay, or BFG, either one. And so it ends up being 36 degrees for that angle. Okay? Then we're looking for angle GAF. Well, you got to think back to right triangles here. Triangles, again, in general, being 180 degrees. We already have a 90 in there, so take out the 90. The other two angles, the other two acute angles, have to add up to 90. Well, we just said one of them is 36, so we would take 90 minus 36 to get the angle GAF at the bottom there. And so 90 minus 36 ends up giving us 54 for that base angle inside of that triangle. Okay? Critical that you see where we got all three of those, because you have to do that over and over and over again in this section.
If you had no idea how to see angle GAF or angle AFG still, man, you're going to be in deep trouble here.
Yeah, you got to be able to see those, guys.
Yep.
So if you're not seeing it here, pause this, go to your book, see some other examples and so on, but you got to see where we're getting those from.
Yep.
Ask questions in class if you're stuck here.
All right, so here's the now that we've gotten an understanding of what apothem is and what the radiuses are and stuff like that, we can get into the actual formula of a regular polygon. And most of the time we use these formulas. You're going to see them most often for things greater than a quadrilateral. I mean, we don't use it that much for anything less than the quadrilateral, because we have all the other formulas for it. You might see it here and there, but for the most part, this is going to be for things greater than a quadrilateral, so 5 up.
Depending on up, yeah.
Yeah. So anyway, so the formula for a regular polygon, there's two different ways you can look at it. You can look at it as 1/2 the apothem times the perimeter. Okay, we use an uppercase P here for perimeter, which is, the number of sides times the side length. Or you can think of it as 1/2 the apothem, okay, times the number of sides times the side length. So basically what P is without calling it P.
Right.
I always think of it as 1/2 AP, and I know that P means perimeter, and it's the number of sides times the side length.
And that's because it's a regular polygon.
It's a regular polygon.
That's why you take just like a square.
Yeah, exactly.
Take 4 times the side length, and so because this is regular, you do the same thing.
Yeah, I mean every side's going to be the same.
Right.
And you can just kind of do some real quick math in your head and figure out the perimeter, no problem.
So those are the you're going to use this formula over and over and over,
Over
again,
and over
guys.
again.
Make sure you
Okay.
got it.
So this is really the newest formula, like where you've just never seen it before.
You've never seen that formula, yeah, for a different shape.
So
Yep.
anyway, so here's an example. It says find the perimeter and the area of this pentagon. Okay, so if I'm looking at this, they give me a radius, they give me a apothem, and that's all they give me. So when I do these, I like to lay out the information I have, and so when I go back to that formula of area of a polygon or a regular polygon is 1/2 the apothem times the number of sides. Well, I know 1/2, it's in the formula. Okay, I know the apothem is 6.5. I know that there are 5 sides, but I do not know the side length. Okay, I don't know I don't know how long each of those sides is going around the 5 times. So that's what I got to figure out. That's the missing piece. And so I can figure that out, and that it's approximately 4.66, because if you look at that diagram, you see you have a right triangle right here. And so if I'm given the hypotenuse and a leg of a right triangle, I know that I can use Pythagorean's theorem and figure out that third side of that right triangle. Now, the thing where you got to be careful here is 4.66 only is half of the side of the actual pentagon. Okay, so you have to double that number. So once I do, 8 squared or c squared minus b squared to get a squared, and I square root all that, I get 4.66. I have to double that, which is about 9.2 roughly in there. And so then I go 9.2 times 5, and that gives me a perimeter of 46.6 units.
Yeah.
Okay?
And again, it's half because that triangle, that isosceles triangle with the 2 radii, got split exactly in half, so it also splits the side in half.
That's right.
The apothem bisects each side of the polygon.
And so now that I know the perimeter, now all I got to do is go back to the top and say, okay, I'm going to do 1/2 the apothem, which is 6.5 times 46.6, like that, and do all the math, plug it into your calculator, 0.5 times 6.5 times 46.6, and you get that the perimeter, or the area actually, that gives me the area, is roughly or approximately 151.45 units squared. Now, where some of you guys may have gotten lost here is on that perimeter thing. Okay, and don't worry, we're going to spend some time with this. This is the most difficult part of the chapter, really, is to be able to do these.
Yeah.
So if you didn't see it, don't lose too much sleep over it. We're going to spend more time kind of getting through this. But this idea of combining perimeter and area is something we haven't really done a lot of either. So anyway.
So just another example, find the apothem in the area. And so we have to find the apothem to get the area here. So first of all, we need to count up how many sides we have. And so this is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10-sided shape. This is a decagon. Okay? And so we're going to plug into that formula in order to be able to come up with the area. So in order to do that, we have to find the apothem first. So we create our central angle there, create the isosceles triangle in there, and find that central angle, because again we split up the 360 degrees. And so I know this is showing 18, but hold off on that for a minute. The actual central angle, there's a line missing in this diagram. The actual central angle is 360 degrees divided by 10, which is 36 degrees. They're ahead of us here on the slide. And so the 36 degrees is the central angle, that full angle at the top. Okay. If you draw the apothem in, then again that splits it exactly in half. And so notice where that green arrow is going. The top angle in that right triangle is 18 degrees. Okay. And so in order to come up with that, then we can use the side of 7 over there, and again that apothem always bisects the side, and so that 3.5 comes from the side length being 7. So we know the bottom of the triangle is 3.5. We know the top angle in the right triangle is 18 degrees, half of the central angle, and so we're going to have to use some trig this time.
Yep.
And so because we're looking for the white line there, we're looking for the apothem. That would be the adjacent side. We're given the opposite side, and so we're looking at tangent here.
Yep.
And so we want to do the tangent of 18 degrees is equal to 3.5 over the adjacent side, the apothem. Okay? And so we'll set that up. Tangent 18 equals 3.5 over A. Remember this from chapter 7. We've got to just flip the tangent 18 in the A. And so it becomes 3.5 over tangent 18. Plug that into your calculator. You're going to get about 10.77 units for that apothem. Now, once we have the apothem, we can plug into the area formula. So the area is 1/2 the apothem, 10.77. The 1/2 comes from the formula. 10.77 is the apothem. And then the 70 comes from the number of sides times how many sides, number of sides times how the length of each side. So the length of each side is 7. Again, we said there's 10 sides to this, and so 70 is the perimeter of this shape. So if you put that all into your calculator to approximate it, it's going to come out to about 377 square units for the area of this decagon. That's a pretty complicated shape to find the area.
Yep.
So that's a good example of what we're doing here, though, guys. Being able to find the area of any kind of shape now.
If you can do these guys where they're giving you just one number on the side,
That's
and
as
then,
hard as it gets.
and then work all the way around, pretty much that's the hardest area problem, period, to really do. They don't get any harder than this.
Yeah.
I mean, because you have to fish for a lot of information here, and that's what we keep coming back to, is you've got to be able to look at this and come up with a valid argument to figure it all out.
And use stuff we used
Yeah,
several chapters ago.
Yeah, it's combining a lot of
That's the
things.
way it is.
Yeah. All right, so here's the last one here. Find the area of the shaded region to the nearest 100th place. So now they want the shaded region, which is the circle. So now you got to find the area of the circle and then subtract out the area of that equilateral triangle. And so they give us the radius, and that's it. So once again, you've got to go back and understand what it is you've got to do here to get an answer. So with any of these composite shapes, guys, list out the two and figure out what operation needs to take place. Oh, that's a 30-degree angle. Let me go back here. The reason why that's 30 degrees is because if you have an equilateral triangle, then that means that 360 divided by 3, okay, is, 180 divided by 3 is 60, and then you got to cut that 60-degree angle in half, okay, to make that isosceles, or that right triangle right there, because that radius is bisecting that 60-degree angle in the equilateral triangle, and that's where they get that 30 from, which is really important because now 30, 60, 90 comes into play here,
easier, yeah.
and you've got to see that right away. I mean, that's what I see when I look at this right away. It's, oh, okay, 30, 60, 90. So if that's 8, then I know that something's going to be something based on that. So anyways, let's go back and lay out what we're going to do here. Okay, so they're going ahead and doing this. So here's the 4. Where this 4 comes from is what I was just saying. We have a 30, 60, 90 right triangle. So if the hypotenuse is 8, okay, then we know that the short leg is half of that. So that's where that 4 comes from. And then the longer piece there, underneath the 30, the long leg, is going to be 4 root 3, okay? And that's what's going to come in there next. And so then for that whole leg across the bottom, which is something we need, that's going to be 8 root 3. And I don't know if they're going to show that right now. Okay, so now they're figuring out the area of the circle, which is pi r squared. Okay, so my radius is 8, so I get that, and I'm going to get 64 pi here. And then I do the area of the triangle, which is 1/2 of 4, okay, times 24 root 3. Now that 24 root 3 comes from the fact that, all right, so this threw me off a little bit. So they're doing the triangle as a regular polygon, so they're using the formula of the area of the triangle is 1/2 the apothem. One second here. 1/2 the apothem times the perimeter. Okay, so 1/2 comes from the formula. 4 is the apothem. That's that right angle going from the side into the center. And then 24 root 3 comes from each side is 8 root 3, and there's 3 of those sides. So 8 root 3, 8 root 3, and 8 root 3 give me 24 root 3. And so now I go through and I'm going to go, okay, the area of the circle is roughly 201.06 once I plug that into my calculator, minus 1/2 of 4 times 24 root 3, which is approximately 83.14 units squared. And then when I subtract those two, I get that the area is 117.92 units. Now, this is one thing that you have to be careful here, guys. You cannot leave this, in order to simplify this all the way down, you can't leave your circle in terms of pi here, or else you can't combine pi with the area of the triangle because they're not on the same playing field. That pi acts kind of like a variable, and so you can't add pi with a number.
Yeah, if we leave these as exact answers, they get kind of complicated because this one would have a pi and a radical in it, separate, and of course you can't combine those and so on, so they look kind of complicated.
Yeah.
But again, we'll practice with several of these guys, so just be patient with these.
Yep.
Okay?